Hi everyone, we're Group 18 and my name is Kaylee Collins.
And I'm Jason Samet.
After a semester of analyzing various structures in ANSYS, we were tasked with combining our knowledge to analyze deformation, stress, fatigue, eigenvalue buckling, and modal frequencies for a bicycle frame. The frame that we were given was a D Carver. Various measurements were provided so that it could be accurately modeled using NX and exported to ANSYS.
As Kaylee mentioned, we first modeled a 2D sketch of the frame with the given dimensions and approximated unspecified dimensions based off standard cross-bike tire widths and frame components.
Two materials were chosen for the bicycle frame, Carver 455 stainless steel and aluminum 6061. Their relevant properties are displayed in the table. 4 loading conditions were selected from literature that simulated front tire bump, rear tire bump, climbing in the saddle, and climbing out of the saddle. The loading conditions are depicted as LC1, LC2, LC3, and LC4, respectively, in the figures. The rider was assumed to be 75 kilograms, and the forces were calculated from computational work.
We began our analysis with a model of beam elements, which was loaded at the specified nodes from our boundary conditions. Preliminary results for each loading condition showed highly concentrated stress near the loaded areas and very little stress at other points in the structure. After these initial results were calculated, which were reasonable in stress and deformation magnitude, a full detailed model of the frame tubing was created. This model was refined at regions of anticipated stress concentrations and contained over 150,000 nodes.
Loading case 1 resulted in a maximum stress at the forks, while loading cases 2, 3, and 4 experienced maximum stress in the seat stay. Eigenvalue buckling resulted in safety factors between 2 and 42, with visible deformation for loading cases 1 and 2. Modal analysis revealed a low natural frequency for loading cases 3 and 4, and could be a point of concern during the designing of the frame.
The first 2 loading conditions displayed natural frequencies over 25 Hz, which is too large to be reasonably encountered by tire bumps. The last 2 loading conditions displayed lower natural frequencies. Although these values of around 8 Hz would not likely be encountered during climbing, the deformation amplitude at these frequencies is reason for concern. In an alternative case, the same frame structure was investigated with the material properties of aluminum. Analysis showed stress values that were not significantly lower than that of steel, but buckling analysis of the second loading condition showed this frame has a much lower safety factor.
Topology optimization for the first loading scenario showed that regions of low stress have a low topology density. While all loading conditions must be considered when redesigning a frame, loading condition 2 is one of the most critical.
To ensure that our ANSYS results are reasonable, hand calculations were performed at critical regions to validate FEM results. For loading scenario 1, the max stress occurs at a concentration on the axle, which is not representative of the fork. Modeling the lower part of the fork as a cantilever beam shows that the stress maxima occur at the same location and the same order of magnitude as ANSYS results. For loading scenario 3, shear stress analysis at the fork tube due to torque shows the handlebar load has a low contribution to stress. However, another cantilever beam analysis at the rear wheel connection again validates the values produced by ANSYS.
Although the tube model showed higher maximum stresses than the beam model, inspection showed that these large stresses occurred at points with stress concentrations. Values elsewhere matched between the models. All relevant values are depicted in these 3 tables. And with that, what questions do you have for us?